And today, wow, we're jumping into something that really stretches how we think about, well, everything. Time, reality itself.
It definitely does.
Okay, so let's set the stage. Imagine our view of the universe is built on these two massive pillars.
Yeah.
Brilliant theories, both of them.
Uh-huh.
One is general relativity, big stuff, planets, stars, gravity, the smooth, predictable cosmos.
The grand scale.
Exactly.
Yeah.
But then there's the other pillar, quantum mechanics. Tiny stuff, particles, probabilities, weirdness, and this spooky action at a distance Einstein talked about.
Ah, yes, entangled.
That's the one, that spookiness. And that's where we start today, because you sent us this fascinating idea.
Yeah.
What if that spookiness isn't just quantum weirdness? What if it's baked into space-time itself? What if particles entangled in space have to be entangled in time, too?
It's a profound question. And it connects these two sort of warring theories in a really elegant way, potentially.
Okay.
So we'll journey from Einstein's spacetime, the whole block universe idea.
Right.
Then look hard at entanglement, some really mind-bending experiments about time, and land on these, well, pretty radical new frameworks for thinking about reality. It's quite a ride.
Okay, I'm ready. So temporal entanglement. Before we get there, we need the foundation, right? This relativistic canvas. We used to think space and time were separate things. What changed?
Yeah, for ages, Newton's view dominated. Space was just this fixed 3D box. Time was this universal clock, ticking the same for everyone. Simple. Felt right.
Very intuitive.
Totally. But Einstein's special relativity just blew that apart. His ideas, speed of light being constant, laws of physics the same for observers moving uniformly, they led somewhere inescapable.
Which was?
That space and time aren't separate, they're woven together. Minkowski, Einstein's old professor, he nailed it back in 1908. He said something like,
Oh yeah, I remember this quote.
henceforth, space by itself and time by itself are doomed to fade away into mere shadows.
And only a kind of union of the two will preserve an independent reality. Powerful stuff.
Exactly. And that union is space-time, a four-dimensional thing. An event isn't just where something happens, but where and when. A point in 4D.
XYZT.
Precisely. And here's the kicker. If you and I are moving relative to each other, my measurement of a time interval might look like a mix of time and space to you.
They get mixed up.
They literally get mixed up. That's the core of unified spacetime.
Okay, so that unification leads to something even weirder, maybe. The block universe. What's that about? Why does relativity kind of force it on us?
Right, the block universe or eternalism. It comes from this thing called the relativity of simultaneity.
Meaning?
Meaning if we're moving relative to each other, we might not even agree on whether two separate events happen at the same time. My now could be your past.
Oh, right, so there's no universal now.
Exactly. The idea of a single, objective present moment just dissolves. So the most logical way to think about it, if relativity holds, is that all moments, past, present, future, they're all equally real. They coexist.
Like a block. A 4D block of spacetime, all laid out.
That's the picture. And your life, my life, the history of particle, it's not a journey through time. It's a fixed path, a world line, already existing within that block.
Like a line drawn through the block.
A timeless, unchanging trajectory. The whole universe as this incredibly complex, static pattern of interwoven world lines.
Okay, but that feels so counter to quantum mechanics, right? The probabilities, the randomness.
It absolutely does. That's a huge tension. But, and this is key for us today, the block universe provides the necessary stage for temporal entanglement. If the whole block exists, then connections across time make just as much sense as connections across space.
Okay, so we have our block universe stage. Now bring in the quantum weirdness entanglement. That's spooky action. How does the block universe view change how we think about that?
Well, let's quickly define entanglement again. It's when particles are linked in such a way that you can't describe them individually. Their fates are tied together no matter how far apart they are.
Like the spin example.
Exactly. A particle decays into two, say, an electron and a positron. Total spin is 0. If you measure one as spin up, you instantly know the other is spin down along that same axis. Perfect anti-correlation.
But that doesn't have to be spooky, right? The hidden variables idea.
Right. Classically, you could imagine they always had opposite spins. You just didn't know until you measured. Like Dr. Bertelsmann's socks, one pink, one green, hidden in boxes. Finding one tells you the other.
Einstein hoped for something like that, didn't he? Local hidden variables.
He did. He hoped QM was incomplete, that there was a deeper, more deterministic layer underneath, something local.
The experiment said otherwise. Bell's inequality.
Precisely. John Bell figured out a mathematical test. Any theory based on those local predetermined properties like the socks could only produce correlations up to a certain limit.
Bell's inequality.
Yep. But quantum mechanics predicted stronger correlations, violations of that limit.
And the experiments. Clauser, aspect.
They did the experiments, measured entangled particles at different angles, and guess what?
They violated the inequality.
Conclusively. Repeatedly. It proved the properties aren't set in advance. It's a genuine, non-local connection. It's real.
But still no faster than light messages, right?
Crucially, no. Alice measures spin up, Bob gets spin down, but Alice's result is random. She can't choose to send up to transmit a message. It's correlation without communication.
Okay, so maybe thinking of them as separate particles is the wrong way.
That's a much better way to think about it. They form a single, unified quantum system, just spread out. A measurement anywhere affects the whole system state description instantly.
And it's about potential outcomes, not fixed properties.
Exactly. Before measurement, the particle is in a superposition potentially up and down. Entanglement locks the probabilities of these potentials together across the whole system. Measuring one actualizes a potential, which instantly defines the only remaining potential for the other.
Okay. Seeing it as a constraint on probabilities.
Yeah.
That feels like it could apply across time, too.
That's a conceptual leap. If entanglement is this fundamental constraint on potential outcomes within a system, why should that constraint only apply across space in the block universe?
Right. So how do physicists make that leap formal? Temporal entanglement.
Yeah.
What does that look like mathematically?
One approach is this idea of space-time duality, kind of swapping the roles of space and time in the math.
How does that work?
Well, using a technique called analytic continuation, they can, roughly speaking, replace a spatial distance in some equations with an imaginary time interval.
Imaginary time. Okay.
It's a mathematical trick, but it lets them calculate something called time-like entanglement entropy. It's basically a measure of how correlated a system is with itself at different points in time.
So measuring the entanglement along its own world line, in a sense.
That's a good way to put it. It formalizes the idea that entanglement isn't just spatial.
And then there's entangled histories. That sounds even wilder.
Yeah, that builds on Feynman's path integrals. You know, the idea that a particle takes all possible paths between 2 points.
Right, the sum over histories.
So entangled histories suggest that these entire paths or histories can be entangled. A system's properties at one time can be correlated with its properties at a different, maybe much later or earlier time, because their whole evolutionary paths are linked.
So not just linking two particles now, but linking a particle now with itself then, or even across different moments in different particle histories.
Exactly. It shifts from correlating what across space to correlating when and what along a timeline, or even across timelines.
Okay, deep breath. And the most radical version, entanglement of the vacuum itself. Empty space isn't empty.
Yeah. Empty space is complicated. Quantum field theory suggests the vacuum is fizzing with virtual particles and has this incredibly rich entanglement structure.
Entangled how?
There are calculations, particularly involving accelerating observers, that show entanglement between regions of spacetime separated in time, like between a past region and a future region from the observer's perspective.
Whoa.
If that's right, it means the non-locality we see with particles is just an excitation, a ripple on top of an already fundamentally entangled spacetime.
So entanglement isn't the weird add-on, it's the foundation.
Potentially, yes. It could be a core principle of reality itself.
Okay, let's try to pin down the difference again. Spatial entanglement. Two different particles, same time, linked across space. Tested by Bell tests. Temporal entanglement, maybe one particle at different times, or particles that don't coexist, linked across time. Probed by these delayed choice experiments.
That's a perfect summary. You've got the core distinction, and it sets us up for the experiments.
Right, because this isn't just theory. There's experimental evidence, isn't there?
Yeah.
Stuff that really challenges our notion of time.
Oh, absolutely. These experiments are where the rubber meets the road, and they are deeply weird. The famous one is the delayed choice quantum eraser. Kim et al., 1999.
Okay, walk us through it simply. Double slit.
Right. Photon goes through a double slit. Then a special crystal splits it into two entangled photons, a signal and an idler.
Signal goes straight to a detector, D00 records its position.
Yep. The idler takes a longer route. Its path involves beam splitters and detectors set up, so you can either find out which slit the signal photon went through,
Get the which path info.
or erase that information. And the key is the delay. This choice happens about 8 nanoseconds after the signal photon has already hit D0.
So the signal photon's fate is supposedly sealed. It's hit the detector, but then later something happens to its twin. What do they see at D0?
And if you just look at all the dots piling up on D0, it's just a blob. No pattern.
Okay.
But then they use the idler the future information to sort the D0 data.
Post-selection.
Exactly. They look only at the signal photons whose idler twin had its which path info erased, and boom, an interference pattern emerges from that subset of past data.
Wow. And if the info wasn't erased?
Then that subset shows no interference, just the blob. It's as if the signal photon knew whether its future twin would reveal its path or not.
But it's not sending a signal back in time?
No, still no signaling. But it strongly suggests the past pattern is somehow contingent on the future measurement. Mind-bending.
Okay. What about entanglement swapping?
Yeah.
And steering into the past?
Right. Imagine two separate pairs of entangled particles, A, B, and CD. A and D start totally unrelated.
No connection.
Then you do a special joint measurement on B and C, the inside particles. This measurement projects the outside particles, A and D, into an entangled state.
Even though they never interacted.
Never interacted, no shared past. And you can even set it up so this happens between systems that don't overlap in time. Again, hinting at these connections across time slices.
Okay, this leads to the big one, right? The delayed choice entanglement swapping experiment. Ma et al., 2012. This combines everything.
It really does. It's the culmination. Two pairs again, 1, 2, and 3, 4. Photons 1 and 4 go to Alice and Bob. They measure them first. Done. Recorded.
Okay.
Photons 2 and 3 travel a much longer path to Victor. They arrive maybe 500 nanoseconds after Alice and Bob are finished.
Significant delay.
Definitely. Now Victor gets 2 and 3. He uses a random number generator to decide what to do. Option A, perform a Bell state measurement, which entangles 2 and 3 if they weren't already.
Okay.
Option B, measures them individually. A separable state measurement keeps them separate.
And the result? Remember, Alice and Bob's data is already in the can.
That's the astonishing part. They compare all the data later. If Victor chose to entangle 2 and 3, the Bell measurement, then Alice and Bob's past data shows strong quantum correlations, as if 1 and 4 were entangled all along.
And if Victor chose not to entangle them?
Then Alice and Bob's past data shows only weak classical correlations. No entanglement.
So, the entanglement status of particles that no longer exist is determined by a random choice made in their future.
That's what the data shows. It's incredibly hard to explain without some kind of time symmetry. It's the strongest motivation for this view.
Okay, so the block universe helps here. How does it let us avoid paradoxes? It feels like changing the past.
Yeah, the paradox question is crucial, but retrocausality is the wrong word, really. It's better to think a temporal correlation or global consistency.
Meaning?
In the block universe, the experiment isn't changing the past. It's revealing correlations that were always part of the static 4D pattern. Victor's choice isn't an action flowing backward. It's just one coordinate in the overall geometric structure that exists timelessly.
So the entire experiment, start to finish, is one fixed pattern in the block.
Exactly, like a complex sculpture. The measurements are just ways of looking at different cross-sections of this pre-existing sculpture. We see a temporal global coherence.
Okay, that framing helps avoid the paradox feeling. But it does strain the standard quantum interpretation, right? Have new interpretations emerged that embrace this time symmetry?
Absolutely. The standard view feels very strained by these results. A key precursor was actually Wheeler and Feynman's absolver theory, way back in the 40s.
For electromagnetism.
Yeah. Maxwell's equations work forwards and backwards in time. They allow retarded waves going forward and advanced waves going backward from the future.
Advanced waves from the future.
Sounds weird, right? But Wheeler and Feynman propose that when something emits light, it sends out both. The forward wave hits an absorber in the future, which then sends an advanced wave back to the emitter, arriving right at the moment of emission.
A handshake across time.
Exactly. A time-symmetric two-way exchange forming the interaction.
Okay, that's cool. How did Kramer connect this handshake to quantum mechanics, the transactional interpretation, TIQM?
Kramer ran with that handshake idea for quantum events. He proposed a quantum event as a transaction.
How does it work?
An emitter sends out an offer wave, basically the standard wave function, going forward.
Okay.
Potential absorbers receive this wave and respond by sending back a confirmation wave. That's complex conjugate, going backward in time.
Backwards again.
Yep. Then, a transaction gets stochastically established between the emitter and one absorber. It forms a kind of standing wave across space-time between them. That completed transaction is the actual quantum event, the transfer of energy, momentum.
And this happens when?
Kramer calls it pseudotime. It's not our normal time, it's in a temporal sequence. This whole handshake is explicitly non-local and provides a physical mechanism for entanglement correlations. It also explains the Born rule for probabilities and wave function collapse naturally.
Interesting. What about the two-state vector formalism, TSVF? That also sounds time-symmetric.
It is. Developed by Aronov and others, standard QM uses one state vector evolving forward from the start, pre-selection. TSVF says you need two vectors for a complete description. One evolving forward from the past initial state and another evolving backward from the future final state, post-selection.
Describing things from both ends of time.
Precisely. It's tailor-made for analyzing these delayed choice experiments. It naturally incorporates information from the future measurement outcome. It leads to ideas like weak measurements, too. It frames reality as a story written from both beginning and end.
Okay, so if we compare transactional with the standard Copenhagen view, wave function, physical offer wave versus just math tool.
Yes. Collapse. A temporal transaction versus observer-triggered event.
Right. Time. Fundamentally symmetric versus asymmetric arrow from measurement.
Non-locality. Physical handshake versus just spooky action.
That really clarifies the shift in thinking. TIQM embraces the time symmetry.
It provides a much more coherent narrative for these phenomena, I think.
Which brings us back to the big one. Paradoxes. If the future is correlated with the past like this, doesn't that let you, kill your grandfather?
The classic paradox. But again, it's about a temporal correlation, not controllable retrocausality. The fundamental laws act like consistency rules for the whole spacetime block.
Okay.
And these time-symmetric views are paradox-proof for two main reasons. First, no signaling.
Right. Can't send messages back.
Exactly. The outcomes are random. You can't choose to send the kill grandfather signal, so no causal loops.
Okay, that's critical.
Yeah.
And the second reason?
Quantum probability. Even if there were some subtle influence, it's probabilistic, not deterministic. It might slightly change the odds of grandpa tripping, but it can't guarantee it.
It fuzzes things out.
It fuzzes out the causal chain, preventing the sharp contradictions needed for a paradox. So the very quantum weirdness, non-locality, randomness is what prevents the paradoxes.
Non-locality as the universe's paradox shield. I like that.
It's a neat way to think about it.
But if the fundamental laws are so symmetric, why do we feel time flowing only one way? The arrow of time feels undeniably real.
It feels real, absolutely. But that arrow is likely an emergent macroscopic thing, not fundamental to the microlaws.
Emergent from what?
Two main things. First, the thermodynamic arrow. The second law of thermodynamics. Entropy disorder always increases in a closed system.
Eggs breaking, not unbreaking. Cream mixing, not unmixing.
Exactly. That gives a powerful statistical direction. Second, the cosmological arrow. The universe started in a very low entropy state, the Big Bang, and has been expanding and becoming more disordered ever since.
So the universe's expansion gives time a direction.
It provides a global direction. The underlying laws can be symmetric, but the overall state of the universe and the statistical behavior of large systems hides that symmetry from us on our scale. Even our ability to form memories is tied to thermodynamics. It's an entropy-increasing process, so it only goes one way.
Wow. Okay, so pulling it all together. This deep dive suggests temporal entanglement isn't just a fringe idea. It offers a coherent way to look at some really deep physics mysteries.
I think that's right. We've seen the evidence converging. The block universe setting the stage, the math of space-time duality and entangled histories, the really compelling delayed choice experiments, and these time-symmetric interpretations like T2M giving a framework.
And the picture it paints.
It's a universe as a static 4D block. Quantum events as timeless transactions or fixed geometric features within it. Entanglement isn't spooky action, it's a temporal global coherence built into the structure. The laws are like architectural blueprints for this timeless reality.
It's a huge shift.
Yeah.
And it's driving new research, right? Where does this go next?
Several exciting areas. Quantum gravity is a big one. Maybe understanding vacuum entanglement is key to unifying GR and QM.
The Holy Grail.
Pretty much.
Yeah.
Then there's quantum information ideas like quantum blockchains using time entanglement for secure records.
Practical applications, too.
Potentially. But we should also say this view isn't mainstream yet. There's lots of debate, lots more work needed experimentally and theoretically to really reach consensus on what time and causality truly are.
So the journey continues. But it definitely forces you, the listener, to question those basic assumptions. What if our feeling of time flowing is just our limited view? What if reality is fundamentally more connected, more whole, more timeless than we usually dare to think?
That's the provocative thought to leave with.
Indeed. Well, thank you for sharing your sources and for joining us on this really fascinating deep dive.